Let's compute derivatives of the inverse function. There are many ways to utilize the inverse function theorem, and depending on the type of function that you have many avenues to work problems that involve computing the derivative of the inverse. So I want to give you some ideas about that type of computation. So say we have the function f of x equal the square root of x minus 5, and we'll just call that y. And we want to prove that f is 1 to 1 and then compute the derivative of the inverse function at 1. Okay, so first we just do a little bit of college algebra. We can see that the domain of f will be 5 inclusive to infinity, and then of course the range will be 0 to infinity inclusive of 0. So that's just basic college algebra. And so first what we want to do is show that f is 1 to 1. So basically what we want to do is take two values of the function f of a equal to f of b and show that that implies the inputs must be equal. And so of course this is very simple. So this just means that the square root of a minus 5 is equal to the square root of b minus 5. So you can square to get a minus 5 equal b minus 5. And of course the minus 5 is absorbed and we have a equal b. So by definition, f is 1 to 1, so the inverse function does exist. And of course the domain of the inverse function is the range of f, and the range of the inverse function is the domain of f. Now, in order to do this computation, we need to find the actual range value that corresponds to 1 if we're thinking about the inverse function theorem. And so when we have y equal to 1, that just means 1 is equal to x minus 5 square root. But then, of course, just by observation, x would have to be 6. So we have x equals 6. So the idea here is if we're going to use the inverse function theorem without knowing the formula for the inverse, we need to know the corresponding value to the y, which is the x equals 6, which again is in the range of the inverse function or the domain of f. It just depends how you want to phrase it. And so now the inverse function theorem says if we want the derivative of f inverse evaluated at 1, then we take 1 over f prime evaluated at 6. And so of course we need to take the derivative of f since we know what the formula is. So that'll be 1/2 x to the 1/2 times x minus 5 raised to the negative 1/2 power. And of course the chain rule just gives us a 1. And then of course we want to evaluate this at x equals 6. But before I do that, let's just go ahead and simplify it. Everything can reciprocate. The 2 comes upstairs, the radical comes upstairs, and we have 2 square root x minus 5. And if we evaluate at 6, we just get 2 times 1 equals 2. And like I said before, we do this computation without knowing the formula for the inverse. So that's really the power of the inverse function theorem. It can also be used to determine formulas for the inverse function derivative, especially when the function is transcendental and you don't have any algebra open to you. Now, I just want to make a point. Say you were in college algebra and the question was to solve for the inverse function. So once you prove that it was 1 to 1, then you would just solve for x here. So you'd square it out to get y squared equals x minus 5. And then, of course, you solve for x. So x is y squared plus 5. So the inverse function with respect to y is just y squared plus 5. So then you could easily find the derivative of the inverse function at 1 just by differentiating this. You get 2y, and then evaluate it at 1. 2 times 1 is 2. So of course you get the same answer, but that's a lot of work if you're just trying to find the value of the derivative of the inverse at one point. So you need to take a little bit of time to understand how these processes work and how the inverse function relates to f and how the derivative of the inverse function relates to the derivative of f. And we are done.